This demo will showcase some of the Cosmos infrastructure used to implement the Madrid transport use case. The Cosmos infrastructure is generic and applicable to many IoT use cases, and the Madrid transport use case is an excellent example. Our purpose for the Madrid traffic use case is to detect in real time or even to predict situations where traffic deteriorates from good to bad. When this happens, we at the EMT bus company can use this information in many ways. One example is to alert passengers, for example passengers with special needs and their caregivers, about the expected bad traffic to allow for a change in their plans. The ability to do this in a way which is timely is essential, and if this can be done in a predictive fashion, it is even better. Moreover, the definition of good versus bad traffic needs to depend on the context, such as the location and time of the day. For example, traffic speeds of 30 km per hour might be considered good in the city center in rush hour, but very bad on a freeway in the middle of the night. In Madrid, there are roughly 3,000 traffic sensors located in different parts of the city. Manually monitoring these sensors and associated camera images is a very labor-intensive and time-consuming task, and it is difficult to react in a timely fashion. Moreover, traffic patterns constantly change with different weather patterns, roadworks, or even sporting events. It can be difficult to correctly differentiate between good and bad traffic in a manual fashion, and this is why we need Cosmos. On the left, we are now looking at the user interface built by Cosmos, and on the right, there are three command line windows. The user interface shows the monitoring of traffic at 3 locations in Madrid. For each location, we see the traffic speed as well as intensity, which is the number of vehicles crossing the sensor per hour. Soon, we will run the Cosmos machine learning algorithm, which generates thresholds which are used by complex event processing (CEP) to differentiate between good and bad traffic. When those thresholds are crossed, CEP generates an alert. So far, there are no thresholds, so everything looks normal. On the top right command line window, we subscribe to an MQTT topic. This is where the machine learning will publish its thresholds. We will use the middle command line window later on to show the machine learning code. We use the bottom command line window to invoke the Apache Spark Python shell and run the machine learning script. We invoke this shell with a special jar file developed in Cosmos, which allows efficient access from Spark SQL queries run by machine learning to the historical data stored in OpenStack Swift. We now run the machine learning script, which was written in Python using the Spark machine learning library, as well as a Spark SQL for accessing the historical data. Circled in red, we see the metadata search generated by a Spark SQL query requesting data between 16 p.m. and 20 p.m. The machine learning script generates a separate model for each traffic sensor and for each time period in the day. We differentiate between morning, afternoon, evening and nighttime periods. The script iterates through each sensor and generates thresholds for it, and then moves on to the next sensor. It will generate thresholds for the 3 sensors shown here, as well as another 9 sensors in the city of Madrid. We now see that speed and intensity thresholds have been generated for the first sensor. The speed threshold is 42 km per hour and the intensity threshold is 678 vehicles per hour. These values were published by machine learning into the MQTT topic. The current speed and intensity at this location are above the threshold values, so everything is shown as normal. Machine learning is now generating a model for the second sensor. These models are generated using k-means clustering from the Spark machine learning library. In our case, k equal to 2, because we are looking for two clusters to represent good and bad traffic. We now see thresholds for the second sensor. They are 41 km per hour and 513 vehicles per hour. The current speed and intensity at this location is above threshold, so everything is shown as normal. The machine learning script is now continuing to the third sensor. We now see thresholds for the third sensor. They are 33 km per hour and 616 vehicles per hour. The current speed and intensity at this location is above threshold, so everything is shown as normal. The machine learning script is now continuing to generate thresholds for other sensors not shown on the user interface. Note that the traffic data gets updated for all sensors roughly once every 5 minutes. We now see that the traffic data has been updated for all three sensors. The intensity of traffic at the first sensor decreased and is now below threshold, with a value of 660 vehicles per hour. This results in CEP raising an alert in the Cosmos system, and this can be used by EMT for many purposes. For example, to notify passengers near this location or those whose route will come close to it. Machine learning continues to run for the remaining sensors. Cosmos uses a special technique called a silhouette index to determine when the machine learning needs to be run again for all sensors. This is needed because over time traffic conditions change with changing weather patterns, road construction, or even more cars on the road, so the models needs to be adjusted accordingly. We will now give a behind-the-scenes look at the OpenStack Swift object storage used for the Madrid traffic scenario. Here we see a collection of data objects where each one represents sensor data for a certain time interval. These objects are stored in Parquet format and are partitioned according to date. We chose a particular object and use a Swift REST GET request to retrieve it from object storage. Because the data is in binary Parquet format, it is unreadable, but we can notice that it has a schema embedded inside it at the object footer. We now perform a Swift REST head request to see the object metadata. When we originally uploaded the objects to Swift, we added metadata containing minimum and maximum values for timestamps, speeds, and intensities. Circled in red, we see the minimum and maximum timestamps for this object. This allows us to access and transfer only relevant objects when processing Spark SQL queries, which is a very significant optimization. We now take a look at the machine learning script used for this use case. First, we see that we apply different functions according to the time of the day. Note that our script currently uses 12 sensors, but more can easily be added. We now take a look at the function applied in afternoons. First, we see the configuration and use of the Cosmos Spark SQL driver. A temporary table is generated and it is queried for data in the afternoon time period. This data is normalized and then we apply k-means clustering. We then derive the two cluster centers and calculate the midpoint between the centers. This serves as the speed and intensity thresholds between the two clusters, and we publish them to the MQTT topic. In summary, In Cosmos, we have used both real-time and historical data in order to react to live situations in an efficient and context-sensitive way. Multiple Cosmos components work together in order to solve a real-life use case in Madrid.